All right, welcome to The Explainer. Today we are going to break down a pretty fundamental concept in geotechnical engineering, the frequency analysis used in the software Shake. Now, if you've ever wondered what's really happening under the hood of this powerful tool, you're in exactly the right place. So here's how we're going to tackle this. We'll start with the big picture question, then walk through how the calculation actually works, we'll hit on a really key complication, and then we'll tie it all together at the end. Okay, let's get right into it. We're going to start at the very beginning just to make sure we're all on the same page. So when we talk about frequency analysis in the context of Shake, what does that even mean? It sounds super complex, I know, but the core idea is actually surprisingly simple. Basically, think of it like this. An earthquake's shaking is messy and complicated, right? Well, frequency analysis breaks that messy wave down into a bunch of simple, clean sine and cosine waves. It's kind of like taking a musical chord and splitting it into its individual notes. Then the analysis figures out how the ground responds to each one of those notes. Does it make a certain note louder or quieter, or maybe just delay it a little bit? Okay, so that's the idea, but how does the software actually do this? How does it turn that concept into a real calculation? Let's walk through the flow step by step. The whole thing is really a 5-step journey. You start with your input earthquake motion over time. Step 2 is where you use a fancy math tool called a Fast Fourier Transform, or FFT, to change that motion into its component frequencies. But the real magic, the secret sauce, happens in Step 3. You multiply that spectrum by something called the ground's transfer function. After that, you just work backwards to get your final ground motion. So let's zoom in on that step, that multiplication. This is where all the geotechnical magic really happens, and it's all built around this really elegant concept called the transfer function. So what is this transfer function? Well, you can think of it as a unique rulebook for a specific column of soil. It tells every single frequency exactly how to behave as it travels up through the ground. And this is why certain earthquakes cause so much more damage in some places than others. See, if the incoming earthquake waves happen to have frequencies that match the ground's own natural frequency, its resonant frequency, the transfer function has this huge peak, and that means those specific frequencies get amplified a lot. Now, you might be asking, why go through all this trouble of converting to the frequency domain and back? Well, here's the payoff. What would be a really complex calculation called convolution in the time domain becomes a dead simple multiplication in the frequency domain. It's just incredibly efficient. But of course, there's a complication. A plot twist, if you will. See, soil isn't quite that simple, and dealing with this reality is what makes the whole process in Shake so clever. Here's the problem. Real soil is non-linear. And what that means is its properties, like its stiffness and its ability to damp out vibrations, they aren't constant. They actually change depending on how hard the ground is shaking. So that rulebook, the transfer function, it isn't set in stone. It's actually changing during the earthquake itself. So how on earth does Shake solve this? Well, it doesn't try to solve the messy, nonlinear problem all at once. Instead, it gets smart about it. It iterates. It takes a guess at the soil properties, runs the whole analysis, and then it checks the strain, the amount of deformation in the soil. Based on that strain, it updates the properties, and then it runs the whole analysis again, and again, and again, until it all matches up. And this whole clever looping process, well, it has a name. We call it the equivalent linear method. It's a brilliant workaround, you know? It isn't solving the true nonlinear behavior directly, but it's finding a set of linear properties that are equivalent to how the soil would actually behave at that level of shaking. Okay, so let's bring it all home. Now that we understand the process and the clever workaround for nonlinearity, we can look back at our initial definition with a much deeper appreciation for what's going on. So at the end of the day, Shake is doing something pretty brilliant. It's combining the raw computational speed of frequency domain analysis to do the heavy lifting, and it's pairing that with a smart, iterative approach to handle the complex, real-world fact that soil doesn't play by simple rules. And that leaves us with one final thought to chew on. If the calculation method itself is this robust and this clever, where should we, as the people running the analysis, focus our energy to make sure the results are actually right? It kind of suggests that what we feed into this elegant process is just as important, maybe even more important than the process itself.